In this video we are going to talk about inductors, how inductors are designed, how they work, how they interact together, and what are the physical parameters that we can change when we are designing an inductor. So the basic thing is, what is an inductor? When a length of wire is formed into a coil, it becomes a basic inductor. When there is current in the inductor, a three-dimensional magnetic field is created. A change in current causes the magnetic field to change. This turns into a voltage across the inductor that opposes the original change in current. So inductors oppose the change in current as well. So inductors becomes a big problem in electric circuitry, as well as capacitors. Why? Because they all create a magnetic field. So whenever we are designing something, the material that we use, we have to take in consideration how it's going to be affecting the rest of the electronic components on the circuit. So whenever we have something coiled together, it will be an inductor. So let's see what is an inductor and how is it that it's going to be creating problems and how we can take advantage of their energy is stored in them. So basic inductors, the units are Henry. So the units for capacitors were farads, the units for inductors are henries. It's the inductance of a coil when a current changing at a rate of 1 ampere per second induces 1 voltage across the coil. Most coils are much smaller than 1 Henry. So 1 Henry is pretty high. So what makes the inductor different than capacitor was that a capacitor keeps taking care of the charge, while this one is changing depending on the current that it is created. So let's see, the effect of inductance is greatly magnified by adding turns and winding them on a magnetic material. Large inductors and transformers are wound in a core to increase the inductance. So yes, if you decide to go into electrical engineering in power specialty, you are going to learn everything about transformers, and you'll see that a transformer is nothing more than actually an inductor that, depending on how many turns it has, you can step up the current or step down, not the current, excuse me. You can step up the voltage or step down the current, depending on how you play with the ratios of the turns. Practical inductors. In addition to inductance, actually inductors have winding resistance due to the resistance of the wire and winding capacitance between turns. An equivalent circuit for a practical inductor includes these effects as shown. So yes, this is a model representation of what an inductor looks like. An inductor has a resistance from the wires. An inductor has a capacitance between each turns using dielectric as air. So air dielectric is 1, so it would be just whatever the material of the wire is divided by the distance between the two turns that you are making. So this becomes an issue, and that therefore it has to be modeled with a capacitor there. Notice that the winding resistance in a series with the coil and the winding capacitance is in parallel with the both. Why is this important? Because the capacitance of it is represented as a voltage, while the inductance of an inductor is represented or used or dealt with as a current. That's why this is like this. We have different types of inductors. There are a variety of inductors depending on the amount of inductance required and the application. Some with fine wires are encapsulated and may appear like a resistor. Common symbols for inductor coils are, this is the mostly one used, we have just a symbol of the inductor. This is represented like the inductor. If we have something packaged, it will come out like this, indicating that we have an iron core, we have a ferrite core, and of course we have variable inductors. So whenever something is variable, you're having arrow going across, indicating that it is a variable value. Factors affecting inductance. 4 factors affect the amount of inductance for a coil. The equation for the inductance of a coil is, so we have the number of turns squared, we have the permeability of the material used, we have the A, which is the area, the surface area, and then we have the length of the coil. So the inductance is going to come in henries, the number of turns squared, the permeability times the area, permeability of the material used, the area of the wire used, and the length of the wire used. So see, here is going to be the surface area, the cross-sectional surface area, so it's always kind of a circle. This is how we are going to be able to design our inductance or inductors. Here is in case we would do, we would actually wrap up or design our own inductor. So what is the inductance of a 2 centimeter long, 150 turn coil wrapping a low carbon steel core that is 0.5 centimeter diameter? The permeability of low carbon steel is, and they give it to us. So the area is always going to be a circle, so we get it. The turns is going to be a square. The permeability is given to us. The area, the cross-sectional area is given to us. I mean, we find it using the circle, and then we divide it by the length. And so we get that if we have this configuration, we get 22 millihenries. Practical inductors. Inductors come in a variety of sizes. A few common ones are shown here. So if it is encapsulated, it will look like a resistor. If it is a wire one high current, like you will see it like this is for high power. You usually don't see this because they creating inductance and they can pull you in. So if you go to like distribution stations, you would see them, but they are off limits for the regular public. You see this a lot in, if you were to open your laptop in the motherboard, you'll see this inductor configuration there. And then of course you have variable inductors that most of the time we don't know what they are until we actually know what they are, because they look like this. Actually could be a switch, could be a variable capacitor, a variable resistance, or a variable inductance. So we really don't know unless we know the specifications of the design. So how do we deal with inductors? So inductors are pretty more straightforward compared to capacitors. When inductors are connected in series, the total inductance is the sum of the individual inductors. The general equation for inductor in series is just like resistors in series. We just add them up. So here's an example. You have L1 and L2, and they're asking you for the total inductance. So you would add them up, right? And then you get the units in henries. And then if they are in parallel, just like resistors in parallel, it will be the sum of the reciprocals. The reciprocal of the sum of the reciprocal. That is what your total inductance when they are connected in parallels are. So we have an example here. We have 1.5 millihenries and we have 680 millihenries. So this is the idea as we had before. The limiting factor will be the 680 microhenries. So whatever the combination of these two are, it has to be less than that, because it's a pure parallel connected inductor circuit. So we have to follow the same rules as well. And it is. You see, once we do the calculation, we get 468, and that one is smaller than that, so it satisfies that. So this is all we are going to learn about inductors, how to add them and how to subtract them. So that concludes our inductor discussion.